Hi everyone, in this video we are going to discuss the composition of nuclear fuel. So nuclear fuel is essentially enriched uranium. Enriched uranium. So we are discussing a very, very specific isotope, so U92, okay, so 92 protons, but it's actually U235, so it has a mass number of 235. And so when your fuel source is considered to be enriched uranium, that just means there is more than 0.7% of your fuel source is U235. Okay, so that's when we say enriched uranium, it just means that that fuel source, specifically whatever sample it is, has more than 0.7% of the specific isotope U235. Because if you recall, the most common form of uranium is U238. And so what we need to do right now is differentiate the fuel sources of enriched uranium for a reactor or a weapon. So for a power plant, which uses our nuclear reactors, so power plants, they usually have a fuel source that is anywhere between 3 to 5% U235. But for a weapon, their fuel source is usually 90% U235. So the fuel sources that we use for a reactor are significantly less enriched than the fuel sources that are used for a weapon. So some bad guy would have to actually come grab the source of enriched uranium at a reactor and then continue to enrich it over and over and over and over again until they can get to be 90% of U235, all right? So now, how do they actually do this? How do you purify this? How do you enrich uranium? How do you make it so that you're only looking at U235, not U238? All right, so the way they do this is what's called gaseous diffusion. And so we have a lengthy definition here, but I think it's actually a good one, so we're going to go through with it. So a gaseous diffusion is actually when you use your molecular mass to separate molecules in the gaseous phase. And I want to put underneath here that we could be talking about atoms, okay, or elements or something very specific. It doesn't necessarily have to be molecules, but it could be molecules. Gaseous diffusion is applied to a lot of different pieces. And so what that means is that our lighter molecules, and when I say lighter molecules, again, I'm talking about atoms as well. We're just trying to be vague here, very global. Lighter molecules or atoms are going to move faster than heavier molecules. And again, or atoms. And so we've seen this concept before. And so I'm going to try to trigger your memory here when we were discussing this mixture of hydrocarbons and we talked about separating it in a very, very similar manner. So when was that? Okay, what were we talking about? What were we talking about when we use a similar purification process to separate that mixture of hydrocarbons? What was that called? All right, did you get an answer? Hopefully you did, because I've been trying to sneak little hints in there throughout the whole video and this whole semester, but let's see if we remember. But what we were talking about was called a distillation tower. Distillation tower. So if you recall, we use a distillation tower to purify our crude oil. And so we take our crude oil, which is essentially a mixture of hydrocarbons, we vaporize them, we get them all in the gaseous state, and then by molecular weight or by size, we're actually able to separate and purify each and every single one of those hydrocarbons, which is awesome. So when we talk about gaseous diffusion, it's a very, very, very similar concept. We take U235 and U238, we pop them into the gaseous state, and then we try to separate them by size, okay? But that's not actually the best description of how we purify our nuclear fuel. So let me go through a very complete, but hopefully short, explanation of how we do this. So we start off with uranium ore, which is UO3. And basically what we do is, with a kind of a complicated reaction that I don't expect you to understand, we can convert this to something called UF4, all right? So now UF4 is something that is very neat and it's helpful for us, but it's actually UF6 that is the most helpful, and it's the easiest for us to use gaseous diffusion to purify or in order to create enriched uranium. And so what we do is we take UF4 and we treat it with fluorine gas, and we create something that's called UF6. Now, colloquially, this is what we call hex, okay? So people will just say UF6, that sometimes they'll just refer to it as hex. So if you ever hear that, that's what they're talking about. So now, UF6 has a really, really neat property, and that is that it sublimes at 56 degrees Celsius. And so now, if you recall, sublimes is when you go from a solid to a gaseous state. Think about dry ice, that's always sublimation. So when it's going from that solid state to the gaseous state, okay, sublimes. All right, so what we can do then is we take UF6, that is in the solid state, and we add heat, so we're forcing it to reach the 56 degrees Celsius, and it immediately pops right over to UF6 in the gaseous state. Now, UF6 then, once it's in the gaseous state, we can separate all the different isotopes of uranium in those specific molecules by using gaseous diffusion. And so what we can do is take U-235F6 and U-238, which is going to be slower, right, because it's bigger, slightly bigger, just with a few more neutrons, but this is going to be slower. And so what we can do is, using gaseous diffusion, is actually separate out these two molecules. It's kind of neat, right? You're like, no, lady, be quiet. But I think it's really cool. And so we just use this neat property to actually purify it. Okay, so now, once we have our U-235 of F6, that's what we take. That's what we start with by using our nuclear fuel, and that's how we do this, using gaseous diffusion, to actually separate this out, and we get our fuel source, because we need our enriched uranium. Remember, for a reactor, you want somewhere between 2 to 5% of the U-235. So now, once we have this, we're able to put that into our fuel rods, and we'll use a different video to talk about that. But what I want to talk about now is the opposite, so our depleted uranium. So it's DU is usually what it's called, or depleted uranium. And depleted uranium is essentially the U-238, and it's something that's spent, or it's done, or we have no use for it anymore. And it essentially is stored all over the United States. We have it all over, all these different states, all over the country, okay? So now, what do we do with it? Do we just store it? Do we leave it? Do we hide it? What do we do with it? Well, currently, we have two main uses for it. The first one, which is kind of an interesting use for it, is we use it in something that's called armor-piercing munitions. So the military uses it. And so they're able to turn it into a very neat weapon that can pierce armor. So it's a very, very dangerous, very powerful, okay? The second one is we can use it to actually create plutonium. So this is a really neat mechanism. And so instead of starting with uranium-235, like we've been talking about this whole time, you start with uranium-238 and you treat it with a neutron. So very high energy neutron. Now, immediately what happens is your uranium turns to 239, which is incredibly unstable. So it barely lasts, not even for a second, just barely create it. And that automatically goes through beta decay, and it creates neptunium, which is NP. This has 93 protons, and it has a mass number of 239. And so in order to balance this equation, we have to give off an electron. So this electron, it looks like this. There's a -1 and a 0. Now, the thing that we focus on is neptunium. So we take neptunium again. I'm just going to rewrite it so that it's a little bit more organized. 239. And now this also goes through beta decay. And so almost instantaneously, this then turns and converts itself into plutonium, which is 94 protons, and it has a mass number also 239. So in order to balance this, we need to add our electron again. Plutonium is dangerous, okay? This is dangerous. If we're not using uranium to create a nuclear weapon, we're using plutonium. And in fact, plutonium is what was used in the bomb that was dropped on Nagasaki. Okay, so we've talked about two different things here for our fuel. We've talked about U-235, which is actually used in our reactors, and we've also talked about our depleted uranium, which can be used for armor and weapons, and it can also be used to create plutonium. So here's my question with how I want to end this here. Do you think that we have any type of international security risks, or maybe problems, with U-235 and depleted uranium, which is your U-238, excuse me? Do you think that we have any issues with that, or that we could have any issues with that? I think this is obvious, but I don't like saying things are obvious, but yes, it is definitely an issue. We do not want uranium-235 or depleted uranium just sitting out there for somebody to grab and just start messing around with it to see if they could create any type of nuclear weapon, or maybe something even crazier. So yes, we have international security risks, but the people who are aware of this are very, very aware of this, and we do a lot to try to control things and make sure people don't get out of control. We're going to talk about that in a different video as well, where we have different regulations to try to make sure that every nation is being honest and nobody is secretly creating some kind of nuclear weapon, which would be absolutely terrifying. All right, take care of yourself. Drink water, y'all.